Okay, last presentation of week 2. We're going to go over Pareto graphs, which are really simple. We're going to look at z-scores and empirical rule now that we know how to use our calculators better and how to use StatCrunch. And we're going to start chapter 3.1. So Pareto graphs, z-scores, and empirical rule. Pareto graphs are actually very simple. So these are actually the same two graphs, a little cut off at the top. On the top one, that's the window for the video. It shows frequency. And I cut off on the bottom one, but you can see the categories from the top. They're the same graphs, with the bars shown in a different order. Pareto graphs go with the idea of starting with the highest frequency leftmost and working its way down in descending order. Now, if you had a category like Other, it might actually appear in the far right-hand side and be bigger than one of the prior categories. That's the best they thought they could do. So I made these in StatCrunch using bar plot, and then I picked with summary. You should see if you can duplicate these. That'll get you very good with StatCrunch. And then use the copy command under options of the graph you complete and see what that does for you. It's pretty cool. What are z-scores? Well, we've gone through the idea and the math of how to compute the standard deviation of the sample. We call it S. So it measures how much the data varies. We want to quantify that a little better instead of just saying something like that. So we're going to calculate something called the z-score. The best way I can think to do it with you is to actually go through an example. Suppose the sample mean x bar is equal to 75 and the standard deviation for the sample, we call that S, is equal to 15. And one of the numbers we're using in our data set is 45. What's its z-score? Well, the z-score simply measures how many standard deviations an observation is from sample mean. And remember, it could be to the right or to the left. So if it's to the right, we'll call it positive. If it's to the left, we'll call it negative. To calculate it, we take the sample mean, and from that we subtract the number we're looking at. Once we get that, we divide by the standard deviation, and that's shown below for you. You might want to stop and look at this by yourself. The empirical rule looks at standard deviations on a normal distribution that's symmetric. You see from the graph here, it shows 68% of data between these two vertical lines. Those two vertical lines have been placed one standard deviation from the center of the normal distribution. The area underneath this curve has been made to equal to 1. So if we looked at the area in terms of 1, this would be 0.68%. The next pair of bars further out, at 2 and negative 2, you have 95% of the data underneath that curve. And the last pair of bars are at 3 standard deviations to either side. And that pretty well covers almost every data that you're going to have. So you can think of that as like 99%, and we will get more exact on that. It's shown below here with x bar plus or minus s, x bar plus or minus 2s, and so on. Going to chapter 3, these ideas are maybe new to you, so take some time to go over it and go over it a second time if you need to. Explanatory versus response variables probably would be pretty easy for you if you're familiar with the algebra. They're simply called differently than they were in algebra. Simply put, the response variable is the dependent variable and the explanatory variable is the independent variable. So if you have f of x equal y, y would be your dependent variable, and x would be your independent variable. For instance, if someone's tall, they generally have the ability to jump higher than someone who's short. I think in general, most of us would say yes. But which one of these variables controls the other? Does the person's height control how high they can jump, or how high they can jump control the person's height? You should be aware that not everything makes sense in these terms. I can write a formula where my independent variable is Fahrenheit and my dependent variable is Celsius, but I can also reverse the roles. So this concept is good to use, but it doesn't work for everything. Contingency tables are a little harder to do, so you need actually to look in the book, spend some time on them, not just this. Here's a contingency table shown. We have this category to one side, cold length, how long the person had a cold, and one on the top, whether or not they took medicine. And simply, we have frequency counts for the numbers in here. Where you have one of these columns like yes and a row such as 1 to 3 days intersect, that's called a cell. Along the top, on the right-hand side, along the right-hand side and along the bottom are totals, and these are said to be done in the margins. So you'll hear that word, and that's what it means. But if we look at relative frequencies, we can actually make better comparisons than if we look at the frequency counts. So we've done a couple here. Take a minute, verify these are correct. If they're not, fix them. Let me know. Now suppose we ignored that bottom row of totals and we simply put relative frequencies in the cells. So when I'm looking at 0.82, I'm looking at 82% of the people who had a cold from 1 to 3 days took medicine, and that 18% did not take medicine. That total that you see to the far right is 100%. Now I look at the next row, and 17% people who had a cold from 4 to 7 days took medicine, while 83% did not. The N is shown so that you have some idea what this is based on. I've given you a ratio so you can compare the 82% to the 17%, but I'd like you to finish it out yourself. And that ends it for us.